Hey all, this is the last video for chapter 13, kind of covering the last few parts of it. Two main parts for today we're going to look at in chapter 13. It's actually section point 5, which talks a little bit about solids. Now solids are not stressed a whole lot in this chapter overall in general. It's mainly just kind of covering a few vocabulary terms, a few properties of them, and then kind of going over a few things we've learned already before with solids, delta H of fusion, things like that. And we'll also talk about phase diagrams, and that is going to be important. But the solid stuff, there's not a whole lot to it. Not overly complicated, like I said, just a whole lot of terms. So in a solid, our molecules can't move, locked in place. Okay, since they can't move, with all solids there's some sort of repeating pattern to them. Now I told you guys on our website you can totally ignore section 13.4. It goes into the different repeating patterns and the names behind them. We don't have to worry about any of that. The general term for any sort of solid repeating pattern, we call it a lattice or a crystal lattice. Okay, crystal just meaning solid, and lattice just sort of describes the structure. We have our ionic solids. Supposed to say, oh geez, that just looks ugly. I don't like it. All right, ionic solids. Okay, ionic solids, guess what? Those are made up of ions. Yay! We also have metallic solids. Now we don't spend a whole lot of time talking about metallic bonds, but metallic solids are just made up of metal atoms, right? Not ions, just atoms. And we also have molecular solids. So molecular solids, again, obviously, made up of molecules that repeat in a pattern in some sort of a crystal structure. So a little bit about molecular solids. Their arrangement, I think there's an E in there. I hope I spelled that right. Their arrangement depends on the shape of the molecules. And what kind of intermolecular forces they have. So like whether or not a molecule is tetrahedral, which is a really common molecular solid shape, and then the strength of the intermolecular forces. Obviously the stronger the intermolecular force, the higher the melting point, higher boiling point, things like that. We also have what we call network solids. These are covalently bonded atoms. Okay, network solids in general are very, very tough, hard, with high melting points. And then, of course, high boiling points as well. So that property tells us that lots of energy is required, lots of energy needed to break down the bonds in the lattice. Okay. Now I can change the page here and give you guys a quick example. Two common network solids, or just comparing, right? We have CO2 and we have SiO2. Okay, CO2 we know is carbon dioxide, SiO2 is silicon dioxide. So CO2 is a gas at room temp. And CO2 melts at negative 78 degrees Celsius. Okay, you can have solid CO2, right? It's what we call dry ice. Now, carbon and silicon, they're actually in the same family on our periodic table. Okay, so they do share similar properties. However, the type of bonding they have is vastly different. Silicon dioxide is a solid at room temp. Okay, this substance melts at 1600 degrees Celsius. Okay, huge difference. Okay, so this difference in property is explained by their structures. Okay, difference is their structures. Silicon dioxide consists of a tetrahedral silicon atoms. They're all linked together through covalent bonds to oxygen in a really giant three-dimensional crystal lattice. Okay, very high temperatures required to break that structure down and break down those covalent bonds between silicon and oxygen. So compare that to CO2, that just has weak dispersion forces. CO2 is a nonpolar molecule. The only intermolecular force there is dispersion forces. So those are incredibly, very weak. Okay, so we can kind of add a little note here. Low temp to overcome dispersion. And we said here, high temp to break covalent lattice, the covalent structure. Okay. One more type of solid we have to cover is amorphous. So we also have amorphous solids. Amorphous solids are interesting. If you look down at the molecular level, molecularly they look like liquids. But the forces, the intermolecular forces between them, are strong enough to hold together. A few other properties to them. So since they look like a liquid, there actually is no large repeating pattern. Okay, so in fact there's no pattern. The molecules are kind of all over the place. Sort of describes a liquid. That's what liquids do. But the forces are still strong enough that we still classify it as a solid. A good example of that is glass. Okay, glass is an amorphous solid. Some people actually thought it was a liquid because if you look at like glass panes, like stained glass windows, things like that, the glass would actually be whiter at the bottom than it would be at the top, which led people to believe that the glass was actually slowly oozing and gravity was pulling it down just like a liquid would do, when in fact that's not actually true at all. That's just kind of how the glass was made back then. Glass is still considered a solid, but molecularly it looks like a liquid. There's just no large repeating pattern to it. If you break it, glass breaks into all sorts of random pieces, right? There's no pattern. Okay, those are just kind of some general descriptions of the different classifications of different solids. Again, it's not really all super important. All the important stuff we've covered so far we've already done. The intermolecular forces and the properties of liquids. Okay, really quick, we'll cover what we need to know in section 13.6, which describes a little bit of the physical properties of solids. Now this is, oh geez, that's supposed to say properties. Properties of solids. Okay, a lot of this is going to be review. Okay, You guys know we have our enthalpy of fusion. Remember hearing all about that. That's our delta H fusion. Unit is usually kilojoules per mole. Be mindful of your units. So, simple definition, we already looked at before, but remind yourself, energy needed to melt a solid. Okay. We also have our enthalpy of crystallization. That's not how you spell crystallization. My C is also really big. Okay. Crystallization. Okay. That is the opposite of the fusion. So what do? You take your fusion and you make it negative. Okay. Rarely do we ever have an actual delta H of crystallization. I suppose we could, but we still just call it delta H of fusion, but we flip the sign. So here, instead of energy needed, this is energy released. From freezing. Remember, freezing is it's an exothermic process, so the energy release that we call the enthalpy of crystallization. I'm not gonna leave another space for it, but you could also add to this list enthalpy of sublimation, right? Sublimation is going from our solid to our gas. So that would be the energy required to go from solid to gas. Know your changes of states. Relook up this material from Chapter 6 if you need to. This is when we covered all this. Same calculations, same idea. Okay. We did an example of one in the previous video, so there's really no need to go into any more examples. We've done it before in Chapter 6. It's really just simple unit conversion. Okay, last piece of the puzzle with this chapter, you're going to want to look at the phase diagram sheet. So go ahead and get that out, take a look at it. Okay, if you're looking at your sheet that I had copied for you guys, you've got two phase diagrams on there. I want you guys to take a look at the one on the top. That's just a general phase diagram. It should say figure 12.4. Okay. Every phase diagram for every substance has that general shape to it. All right. Up here on the screen, I pretty much have a very, very similar drawing with similar things labeled. Okay, you've got temperature on your x-axis, pressure on your y-axis. The unit can vary, and usually there are no units, but it doesn't matter. It shows you the pressure-temperature relationship, and it tells you what state of matter you have at varying pressures and temperatures. Okay. Solid is always the section here on the left-hand side, liquid is always the section here in the middle, and gas takes up the section always over here. Okay. Labeled on your diagram, you have the different changes of state, the terms, right? Melting, solid to liquid, freezing, liquid to solid, so on and so forth. That's all on there for you. Some things to take note. The point right here, where you have a solid, a liquid, and a gas all intersecting, that's called the triple point. At that temperature and pressure, you have all three states of matter all existing all at the same time. It's kind of cool. Remind me, I'll show you a demo of it when I get back. It's kind of neat. A little tricky to do. The point all the way up here on the line that separates liquid from gas. At the very end of it, that line dies. It stops. And at that point, we call that the critical point. All right? That's the pressure and temperature. You have a critical pressure and you have a critical temperature. Both of them combined create the critical point. If you have a temperature above that and or a pressure above that, you can't tell whether you have a liquid or a gas. Okay? It's actually called a supercritical fluid. Kind of neat. But the molecules have both liquid properties, they have both gaseous properties. So it's kind of both, and you really don't know which state of matter you have. Right? The pressure is so high that the molecules are so packed together, they resemble a liquid. But the temperature is so high that the average kinetic energy is making the molecules move so fast, they behave like a gas. So you don't really know what you have. Those are the two key points. The triple point and the critical point. Okay, but I want you guys to take note of what the phase diagram tells you. It's kind of neat. It shows you how much like melting points and boiling points, how much they depend on pressure, right? If I keep my temperature, say on this diagram, let's say my temperature is right here, and I keep it constant, okay? Actually, no, I lied. I'm going to make it here. If I keep it totally constant, right, I'm not going to change the temperature at all. If I increase my pressure, if I move up, I can actually change the gas to a liquid. If I keep increasing the pressure, I can change the liquid to a solid, all at the same temperature. It's very, very interesting, okay? It kind of just shows you the idea that we get so locked into things go through different phases at different temperatures. But that's because we all conduct those experiments and all those thoughts and everything all at the same pressure. But if we really start altering pressure, we can really change states of matter. And it shows us how low the pressure has to be in order to sublime or deposit a substance, right? If I'm all the way down here to really low pressure and a low temperature, I got a solid. And if I keep it at that low pressure and increase my temperature, I can go straight from solid to gas. Also kind of interesting. Okay, that's your general phase diagram. Be familiar with it, okay? A lot of questions, like they'll give you this diagram, it'll be blank. It won't have anything labeled, it'll just have these lines. And it'll just have like letters labeled different places, A, B, C, D, and E. And it'll ask you, hey, what does E mean? What's going on here? What phase of matter do you have here? Things like that, okay? All right, now the reason you've got two phase diagrams is, well, the first one is the general phase diagram, and the one underneath it is the specific phase diagram for water. And I wanted to point out the difference. If you guys look at the phase diagram for water, which is now figure 12.5 on your sheet, you'll notice that the solid-liquid line goes back. It has a negative slope. Okay, it doesn't go back a whole lot, but if you look up above, in the first phase diagram, the solid-liquid line is a positive slope. Okay, it's going forward. But water's goes backward. Water's the only substance you have to worry about that does this. Okay. It's basically the idea that, here, I'll make a little note of it, okay? H2O diagram, solid, liquid line, goes back, okay? And this is due to the solid, H2O, is less dense than liquid. Okay, that's the reason that occurs. If you guys look on your phase diagram, for water, if you look at that that -1 line on the temperature where it says -1 degrees Celsius, if you go up that line, you go from gas. If you keep increasing pressure, you go from gas straight to solid. And if you keep increasing the pressure, you actually turn your solid into a liquid. It shows that the liquid molecules are closer together, they're packed tighter than the solid molecules. Okay, which again goes back to the idea of density. It's all due to the fact that solid H2O is less dense than liquid H2O. So as you keep increasing pressure at a constant temperature, you turn the solid into a liquid. Okay, liquid is the most dense state of matter for H2O. Okay. Other than that, everything else is the same. Critical points right up, in the general place where it should be. The curved lines represent the solid gas line and the liquid gas line. Your triple points on there as well. But be mindful that the slope of the solid liquid line is different for H2O. All right. That's all there is to it. You guys can read the section on phase diagrams. It's actually pretty short. That certainly wouldn't be a bad idea. It's the last section in the chapter. It is section 13.7 is the section on phase diagrams. Give that one a read. It also has the phase diagrams in there, examples of it. Highly recommend doing that. So you guys want to grab that right now. It's kind of a short video. So you're more than welcome to do that. Get started on your homework, work on the problem set, and be prepared for your quiz, which is coming up. All right, guys. Good luck. Let me know if you need anything.
Made with Doodlecast Pro.